and since we spoke on the subject with Fyodor, it might be that in a few months it will be obsolete, because and this is actually it's a long project with Matthias Schütt from Hanover, with Victor González Alonso from Hanover, and also other people. So let us start. So at first I will give two general talks that are on the subject. Then I will discuss Seger's beautiful work on quartics. I will also discuss some notions he introduced. Then I will essentially show what we did, and then I will also discuss work of progress that was essentially the motivation for the whole project. We wanted to do this. And somehow we started from reading quartics, but the arguments on quartics were hard to follow. If I have time, I also discuss something strange, which is Cleb's formula. It's a very classical paper from 60s or 1860, and this also kind of is slightly disputable. So there is this classical paper in the awek. You have a small projected surface. You have polarization, say h small is square of h. You take a reduced curve. You define genus in this. You define this g minus 1 as union of geometric genus of all the components. One is subtracted in each case. You define delta as the intersection of this C with your anti-divisor, and then you get this orbibundle inequality, which should be true for every alpha between 0 and 1.
So you don't assume the curve to be model or anything?
No. Originally Miyaoka just wants the curve to be reducible, but then he says actually there is a kind of statement, kind of proof, and then he says essentially all I want is, he makes no some assumption of this curve. We don't care.
What is the advantage of changing the definition of the genus?
When he's constructing this orthogonal object, he thinks exactly this one for things to work. This paper is pretty hard to follow, and I will not be using this till the very end of the talk, but I feel compelled to justify why I will be doing this in a very classical way.
So, and what is alpha?
Excuse me?
What is
It's
alpha?
any parameter between 0 and 1.
0 and 1. This one should code for everything between 0 and 1. This is the statement. And then, in this 2009 paper, he wants to use this inequality to count lines on a surface. That's the idea. So at first, by he wants to bound the square of C, and then he starts the game. So let's do it for the KT surface. Let us assume that this KT contains certain number of lines, and that C is just the union of all lines. So I have a reduced divisor, all components are smooth, all intersections are transversal, and it's just the have. Then G minus 1 becomes minus number of lines by the very definition, because I am adding minus 1s exactly L times. Delta is 1, this is just the definition of the line. Now line is really the curve which intersects my polarization with x to 1. And then the whole inequality trivializes. I can come back to the previous slide, here. Essentially this one will suddenly become 0, here I will have this else, this will be 0, here this will be 0, here I will get 72. So most of this story suddenly becomes trivial. This is this point. And I want this parabola to behave well between 0 and 1. That's the point of Miyaoka. So the lowest point is, and this is kind of linear calculus 1.
So S is key 3 and I is the number of lines.
C is now union of all lines. You need to apply this algebra
on S in the second line. Number of
on
lines.
S. I'm sorry, on S. Shame on me. So now you take this parabola and you look for the lowest point. And you are lucky because the lowest point is this one. It's indeed between 0 and 1. Okay. And then you suddenly want to play with this inequality. You need this thing to be non-negative. Okay? That's the point. Miyaoka's. Okay.
So what are the two parameters? alpha is one parameter and the other parameter is what?
L is now the number of lines. H is the self-intersection of the
Oh, you're talking about the parabola. The parabola is in the plane. What are the coordinates in this plane?
Right, I'm sorry. The parabola is given by y equal x squared divided by 2 times this minus 6 times x times that plus 7. Yeah? I mean, this is how it
It's a parameter, so it's an equation in alpha and I.
No. The parabola is the graph of this function.
of this function as a function of alpha. Yeah? Inequality of Miyaoka inequality is about alpha. I want the graph of this function to be above x-axis between 0 and 1. Okay? So I
It's
have
a minimum of the function.
exactly. So I want this thing to be positive. Miyaoka wants. So you have to solve this one, and what you get is this one. Sorry, I don't count it now. But you have to multiply, divide by L. Get it? It's so
How did you get? So you divided by L.
exactly what Miyaoka wrote, not me, but so the final outcome is this one. You get a bound which reads 24h above divided by h minus 4. Okay?
So what about h equal to?
So 2 and 4 somehow, this technique for 2 and 4 will not work. Yeah? You cannot play it. Yeah? I mean, for h equal 2, you are kind of, you divide by something negative, so it's not cheating. Mathematics is still true. Yeah? Between this step and this step, it's the both sides, so it's okay. But yeah, you just get that L is non-negative, and this is not a discovery. Yeah? So anyhow, this somehow shows that this modern, beautiful technique that actually originates from work of Fyodor doesn't work for hypersurfaces in P3. Yeah? I mean, the general inequality works, for instance, if you have a surface that's embedded canonically, and then you can play the same game for queen groups. But again, you will get h minus 5 in the denominator. Yeah? Whatever the magic behind this fact, it's just a fact. Yeah? It should be pointed out in the same story that we know very little about the question to what extent this boundary works. Yeah? For instance, it would be nice to know that asymptotics. If I take K trees and I let the polarization to have very high degree, that indeed this is 24, that's kind of limit. Yeah? But this is also on.
So can you remind me, because this is a program of being representation. I is the number of lines.
Yes.
And H
Is the polarization on the K3 surface.
Degree of the polarization.
Okay.
Yes, and for quartics I have 4, for sextic 6, for optic 8, and so on.
So this is, but this is we are still on K3s.
Now it's about K3s. Now it's about K3s. I apply inequality on K3s. Actually, Miyaoka can apply this gadget for conics, for instance, and he constructs examples in which the bound is really sharp, but not for lines. Yeah? This paper is actually addendum to this classical paper on this bound inequality. It's very short, and it also contains a construction of examples which are really sharp. None of them about lines. Okay? If you want to play, for instance, with optics in P5, yeah, then the bundle will give you some 40. The bundle will be around 48. Yeah, and there is now example. Alex Zekiarek was in Hanover in July, and then he played. So there is, for instance, for optics, the best known is 40. A surface with 40.
What is an optic in P5?
I mean, intersect three quadrants. Yeah. Okay, so essentially it's kind of. So now we want to do vortex, hypersurfaces in P3. And then this story becomes absolutely classical. This is what I guess everybody more or less knows. This is work of Salmon, Klepsch, all those great people, Liouville. Starts with product of 2 copies of P3. Then you want your surface to be given by an equation. You define these TJs. Yeah, so essentially, first T1 will be embedded tangent bundle. T2 will be given by associating to each point the quadrant given by the Hessian, and T3 is given by the form of degree.
I don't understand. It's not a surface. You call it S, but it's a hypersurface.
So S is hypersurface in the first copy of P3. And you want to count lines on this hypersurface. And for this, you go to P3 times P2. Okay?
So, okay, F is a function of W. Okay, understand.
Okay? That's the idea. I want to count lines on this surface, say OBE at least 4. And for this purpose, I add an extra copy of P3. And then I take a set of zeros. Of course, on this P3 times P3, I have these two divisors or classes, and then I know how these TJs are expressed by those classes. Yeah. My surface is of degree D, so this generator is degree D. I compute partials, so this is D minus J, and I get this J on the other. Okay.
Okay. So you just take the first, the second and third derivative.
Exactly. You take what it used to be called polars, and I'm not mistaken,
Yeah.
in the classical geometry. Yeah? I don't know where this argument comes up. There is now the book on intersection theory by Isaac Harris called 3 to 64.
But these are the set of zeros in P3 times P3.
Exactly.
Mm-hmm.
So now the next step is, for instance, if you check how these four objects behave, the intersection is really a surface. Yeah? There are no three-dimensional components. At least if you assume S to be small. Yeah? So then you may speak about intersection cycle in the sense of cell. Like you write the linear combination of irreducible components of this intersection with this Tor coefficients. Then, this is a little bit of work, but this is again pretty elementary. You can check the diagonal, this is now S on a D, comes up in this intersection with multiplicity 6. This is essentially playing with Euler identity a few times, and you get this 6. Yeah? There is this paper by Kolar on Shemeredi prototype theorems, where he uses what I'm going to speak about now, and he does not do a complete computation, and in this case this 6 is missing. Yeah? But he just says it can be done this way. For him it's just an important fact. So anyhow, what we have done is pretty clear. Yeah? I take my surface, I take a point, and then at first I take the tangent space, then I take two lines which are given by vanishing of this quadrant, which are the two lines with intersection at least 3, and then if I am lucky, maybe there is a line with intersection 4 at this point. And this is exactly what happens if these things intersect. Yeah? On the other hand, of course, as I have written here, I have for free each copy of the point of the surface. It's unavoidable in the way I did it. Yeah? So now I want to take this thing and subtract 6 times the diagonal. I will get still a cycle, and I will try to cut it with a hyperplane section and project on the first factor.
And that's why
But if the surface is developable, then it doesn't have the expected dimension.
Of course, but I assume degree to be at least 4, and I assume the surface is small.
I assume.
Yeah, so these two conditions are enough for me to be on the safe side. Yeah? And then I do the projection. I want to compute this class. Yeah? So I know what is the expansion of the diagonal in P3.
So W is what?
W is this intersection of those 4 gadgets minus the diagonal.
Is this minus the, okay.
Yeah, so everything is honest because I get a linear combination of surfaces in the product. I remove the irrelevant component, and then I know that over each one of the surfaces I have a line.
Okay.
So by cutting with the hyperplane section, I will get an honest map. When I will be showering, I will be projecting something that's finite. Yeah? No danger of making a mistake. Yeah? So you do that, and then you have to write the expansion of those gadgets. You multiply them. Yeah? So here you will get 6 times d minus 1, because here you have d minus 1, here you have 2 and 3. Then you will get, here you will have d minus 2 times 1 times 3. And finally we get d minus 3 times 1 times 2. Yeah, so you get 11 d minus 18 in this expansion. Yeah? But you are subtracting 6 copies of the diagonal, and you are lucky enough in the diagonal, you are having this gadget. Yeah? This gives you 24. Yeah? Okay?
No, what is SDH?
What is it? Something. Yeah, something. I should say at fast or QC like quelque chose, I don't know. It's so finally, what you will arrive at is this one. 11 d minus 24. If I am kind of doing this absolutely elementary reasoning, it's because it is exactly essentially the best bound that is 150 years old and it's impossible to be in general, yeah? Which is amazing. Yeah? So now what is the claim? And this theorem comes back to Salmon, though he didn't use Chowling's and projection formula of his gadgets. The statement goes as follows, probably it was even known to you. You have a degree surface without root components, then there exists this degree 11 minus 24 polynomial which cuts your surface along the points in which you have a line of contact for. Okay? I did this strange argument because this argument shows how you can essentially compute it for an example. If somebody comes with an equation of a surface, yes, please.
No, it's non-singularity is not limit, it's general.
Yeah, it's general. You can do that.
Why
again.
does it get?
Yeah.
Just the rule.
So for instance, if you take d equal 3, you will get O of 9, which is just the sum of all lines.
Exactly. This is how they got 27 lines for the first time. Yeah. This is exactly what Fabrizio was kind of opposing. It might happen that your surface is the general, like quadric, and then you will get something that vanishes along the surface, and that's it. It's a trivial statement. That's exactly the problem. But on the smooth surface, everything is okay. So this flecknodal divisor is the cycle of this polynomial on the surface, you know? And this gives you the bound. Yeah?
But I don't understand why you get this set and not, I mean, because you're taking it like a closure, and then
it's skewed. I mean, it's set theoretic intersection will be, yeah?
why can't there be like this locus plus another extra line where
I mean, you
there's a line which is in the closure of this other thing. You're thinking that the closure of the locus of lines which have one point of contact over 4. And then you could have these points where there is this line, and then you could have a line which is a limit of these lines. So why can it be that this locus is reducible and the right hand side is contained there, but there could be something else which is just a limit?
Yeah, but you can go to Grassmannian and the intersection number will be semi-continuous, so you have these lines with contact 4, the limit will be also contact 4.
No, because I have a line and a curve. And now there are these lines here which have contact here at one point, and this line in the limit. Could be contained. I can show you. You know it. I mean, I don't see.
Sorry. Now you may try. I mean, once you have this device, you may try to improve it to get better. Yeah. And this is what Segre tried in this beautiful paper. Essentially, he's trying to analyze it a little bit and to find the component which is higher than that. I rightly claim because this bound, which definitely must be true on surfaces of any degree, this bound uses a pretty dangerous place in the proof. Yeah, like he has to show that something comes up with high multiplicity in this cycle and he's doing some mistakes. But maybe it's true. Anyhow,
What is the log D?
excuse me?
What is the log D?
This is the maximal number of lines on the UV surfaces, small ones. Okay?
Those are small, now.
Now they are small. So now I have this, for me line is in P3 a degree 1 curve. If I say degree D surface, the surface is now smooth. And I have these two questions. The first one is what is the sharp bound on the number of lines? And the other one is what is the sharp bound on the number of lines in the fixed line? Okay, it's even simpler. I assume my surface of degree D contains a line, and I want to count the lines along this line. Okay? For degree 3, as I already showed, and everybody knows how to prove it, this is kind of the thing you do with
I don't
students.
understand the question because.
So you assume you fix a line, yeah, you say I will consider all degree D surfaces
So you fix a line outside the surface.
on the surface.
That is the line which is on the surface.
And you want to count the lines that meet the line. So the answer for the first
But the
question,
number of lines contained in the surface and that intersect the line contained in the surface.
Exactly. I'm sorry if I'm kind of, when I write slides I try to avoid many symbols, and this means I'm sorry. So now for degree 3 everybody knows the answer. The first one is 27, the second one is 10. Yeah? And the proof you do with students, if you have students of, say, second semester, is you consider the instance variety, you show that it's smooth, you show that the projection from the instance variety onto the base space is topological cover, and then you just count the degree of the cover in one point. Say you take Fleck cubic or Fermat cubic, you have 27 lines, so every cubic contains 27 lines. Yeah? The gain of this approach is that you see immediately that your surface is singular, yeah, but irreducible, you get less lines. Yeah?
So it's general, yes.
This is on 27, on cubics is the general fact. I mean, singularity is costly lines.
But it continues to.
Yeah, I mean, for cubics.
Continues for the other surface, yeah, or something like that. Yeah, for us,
That's a good question.
sorry.
The problem is it falls in characteristic 2. I will give an example for cortex. It's correct for characteristic, for other characteristic for cortex. Yeah? So anyhow, once everything was known on degree 3, people started to degree 4. Schur constructed his surface with 64 lines, and then Segre gave a proof that the answer for this question is 18, and the answer for this question is 64. Okay? In degree 4. Yeah? So now, both questions are related, and let us analyze this argument because it's beautiful. So the first step of this argument is just doing Fleck nodal, yeah? It has degree 18, so you have at most 80 lines on your surface. Then you say, I have at most 18 lines meeting the fixed line. Then you say, okay, if there is a plane that splits into 4, then you have 18 meeting this one, but 3 are here. So 15, 15, 15, 15, this gives 60 plus 4, is 64. You are done. The next step is, if I have one line that is met by at least 13 other lines, I must get splitting.
So which step are you doing?
I discussed it.
Pardon? I read step 0. So
Once again.
I read step 0, and now you are on step.
So step 0 is just 80, then you get 18, then you get 64, then you get at least 13. And here he speaks of Zeuthen-Segre invariant, that is just Euler number. All you have to do is you have an elliptic fibration, and you compute Euler number of fibers. If you have a fiber with one line, the Euler number is bad, yeah? So you must pay for an extra line. I come back to this. And then, so with this step, I can assume each line on my surface is met by at most 12 other lines, and no 4 of the lines are coplanar.
Okay. I'm sorry, in step 2 you get at most or at least? In step 2.
At most.
Why?
I mean, you have 4 lines, 18 meet a line. So 15 are here, 3 are here, 15 are here, 3 are here. Yeah? But if I have a line, it must meet height intersection. So every line on my surface is on the okay? So it's 64, it's sharp. So now I can assume each line is met by at most 12 other lines. Because if I had 13, I would get a plane, I would use this step, I would get 64. Okay? And I can assume that no 4 are coplanar. Yeah? Okay, so I continue. If I have two coplanar lines on my
Sorry,
surface,
step 1, you want to prove it, or because you just say plane, so now
I will come to this, okay? I will
you
explain
come back
it.
to it.
It's just I want to show what is relation between those two questions. If time allows me, I will kind of speak about kinetics and explain what's going on. Okay. So anyhow, now I take those two coplanar lines. I know that the residual curve on my quartic must be a conic because there are no four coplanar lines. Yeah. And there are two possibilities. If I have one pair with a conic that is not a component of flectonal divisor, I am done. Yeah, because again, I know every line on my surface by meeting a hyperplane section. Here I have 12, so it's 11, 11, 36 plus 2. Yeah, because flectonal have degree 20, intersection with conic will have degree 40. I have already lost 4 points as intersection with those two lines. Okay? So I get bound of 60.
No, don't understand. So if another line will meet either one of the lines, then it's okay, or it meets a conic. What happens if it meets a conic?
Then it's a component of flectonal divisor.
Is a component
Of the flectonal divisor of degree 20. Yeah, I have this divisor.
I thought it was of degree 80.
When I intersect with the surface, it's 80. Now I take this. It's a section. It's an element of OS of 20. So
OS of 20.
yeah. So if I know that it's no component, then it's 40. Yeah. But I paid already for two lines with 4 points. Yeah. So I get 36, 11, 11, and 2. I get 60. Okay. So I can assume that whenever I have a pair of coplanar lines, I pay for it with a conic in the complement. Yeah. But my flectonal gadget has degree 80. If I have 9 pair of coplanar lines, I have 9 conics. So this degree 80 divisor contains 9 conics. So there are 62 lines left at most, yeah? Because 80 minus 18 is 62. I am done again. So the last step is I can assume that my surface contains at most 8 pairs of lines. Yeah? Because coplanar lines, if it contains 9, then the flectonal contains 9 conics. It has degree 80, intersecting with my quartic, so there's no space. But then I can finally use an Evans-Severi lattice. I am on a K3 surface. If I write down the intersection matrix of these 8 pairs of lines, then it's just minus 2s on the diagonal and 1s when they meet. So whatever I try for those pairs of lines, the degree is the rank is at least n plus 1. Okay? So the pairs of lines that meet spend something of rank at least n plus 1. So I have 2n lines for which I pay in the Evans-Severi lattice with n plus 1, and the rest, the other lines, are disjoint. Yeah? They just give me minus 1s on the diagonal. Yeah? So if I just forget about C, I mean over n characteristic, it's 22 minus n plus 1. This is the only possibility for the remaining lines. And this gives me bound of 20. Okay? It's a beautiful argument. I mean, Segre was an absolute. The whole paper is kind of incredible. I can come back to step 1, and the problem is if you take this quartic with this parameter, it is smooth for any characteristic higher than 5. It contains 60 lines. It contains this line. This is obvious because we have the zeros, but 12 lines in the line. So the first step doesn't work. Yeah? It's the mistake of Segre is very subtle. Essentially, he's on the locus of surfaces he considers has 3 components, each of them 6-dimensional. The locus of surfaces where these arguments don't work has 3 components, each component of dimension 6. And Segre believes that moving along one component does the job. That's the problem with the whole argument, essentially. I won't have time to discuss it. But anyhow, so the first plane is false.
Can I ask how do these 20 points are distributed along these lines? I mean, 20 points.
Yeah, I answered this question. So now we can kind of, I'm too slow, sorry, maybe I'm not aggressive enough. Okay, so I want to now to answer the play with question 2. I fix the line, I fix the degree, I will show how we found the surface with 20, and then I will give another argument, which is completely trivial how to get 20. Completely elementary. Okay?
But another argument for 64.
Okay, I mean, at first I will give an argument using elliptic fibrations for this 20 and explain how to get 64 from it. And then if I have time, I will introduce a new gadget. This is some kind of plate with, and we give this 20 for free. It's really elementary to get the maximum of 20, and you can apply it in higher degrees, because it's so simple. Okay? But at first I will do the elliptic fibration, because I think it's a really it's a beautiful argument that answers this question about configuration. So okay, I can fix my line. I can count the residual line. This way I will get the vibration. I assume my surface to be smooth, so there is no problem. It's an honest vibration, yeah, along the line, it works. Essentially, over a point of P1 that gives me a hyperplane, I consider the hyperintersection and remove that. Okay? That's my vibration. Of course, if I have a line which meets my line, then automatically it's a fiber, given by the plane spanned by the two lines. And then Segre had this idea that a line will be called the line of the first kind if it intersects the smooth fiber in no inflection point. So the condition is he wants one smooth fiber, such that the line does not run through its inflection points. Yeah? Every fiber has its inflection points, and then your line may run through it, may run not. Yeah? So he wants one fiber of this kind. Otherwise, we land on the second kind. And this is actually his argument. It's the only argument that works for any degree and gives any kind of bound for the second question. He says if line is of the first kind, then it's met by at most 80 minus 14 other lines. Yeah? And the argument is beautiful, simple, trivial. You can explain it to students. So at first you take just this curve, so degree d minus 1. Then you restrict the whole story to the line you started from. And now, on one hand, if you have an extra line on your surface, then it will meet your old line in one of the points given by this equation. On the other hand, it will meet your line in inflection points of this curve. But you can compute inflection using Hessian. Yeah? So the answer is, you have this matrix, you restrict it to your line you started from. You can count the entries with respect to lambda, the degrees, they are like that. Lambda is the parameter that describes the hyperplane sections. And then all entries are of degree d minus 3 with respect to those coordinates on the line L. The Hessian is of this degree with respect to x1, x2, and 5 with respect to lambda, because I have 1, 1, 3, 1, 2, 2, yeah, it's 5. And then all I have to do, I am looking for parameters for which these two have common roots. And so it's Sylvester matrix. I know that there is one place where they have no common root. So the resultant is not identical as 0. Yeah? It has d minus rows given by the first one, 3d minus 3 given by the second. Its degree is bounded by this number. And this is our ad minus 14. Okay? There is no chance to improve this bound, to get this bound for all surfaces, because a long time ago when I was playing with Miyaoka bound on disjoint lines, I kind of came up with these surfaces, and they contain d times d minus 2 plus 2 lines and need a fixed line. They are beautiful configuration. Somehow they violate various conjectural claims. Yeah? So in general, the number of lines that meet a fixed line should grow quadratically. Yeah? And this bound is linear because you make this assumption lines of the first time. Okay? So now I want to come back to quartics, but somehow this assumption that lines of the second kind.
But your example with 20 lines was different, yeah, because 4 times that, 2
yeah, this one is harder to find. But I will explain how it comes. It's once you know how to look, you find it. So anyhow, the first thing you do when you see this problem with second kind is you write an equation. And condition on the second kind is completely trivial. It's solving an equation for coefficients. You do it with computer, and the computer tells you sorry. Maybe he tells something stronger, but this is the original version. Yeah? And whenever a computer behaves this way, normally the problem is you have too many components. You should stratify the problem. Yeah? And this is what we did with Matthias back then when we were doing this. So the idea is you have this morphism, you restrict your vibration to your line. You get a degree d minus 1 more, and it has ramification divisor by Hurwitz. Yeah? You have a map from P1 to P1, it has to ramify.
Sorry, what is the map?
You take the vibration, so you take the vibration given by hyperinsections.
Yes.
You get degree d minus 1 curves. Each of them intersects your line in d minus 1 points, maybe less. You take this restriction. And then the idea is that you will speak of ramification type of the line by specifying the type of the divisor. Okay? Yeah,
So L is not the map, but this, I mean, L is not the line, but this intersection divider.
and is now, it's all the time it's the same line, the one I started from. I take the line, and then I restrict the vibration to the line. Yes, so over each point of V1 I get d minus 1. It's a d minus 1 fold cover of P1. So by Hurwitz has this ramification divisor, and then I can count the points. And I will speak of a fiber of this vibration as ramified or unramified if this map is ramified respected unramified. In other words, a fiber is unramified if line meets the fiber in d points. Yeah, otherwise it's ramified. Okay? And this characteristic is 0. So for quartics there are 3 possible ramification types. This one, and this one. Yeah? And then I come back to quartics. Now my vibration is given by degree 3 curves. So I know what's the sum of an only number of fibers. I can recognize singular fibers, and I know that every fiber has 9 inflection points. I can classify singular fibers. And now there is huge body work of Kodai, there are lots of possible fibers, but I am lucky, I have just a few possibilities. I have nodal cubic, conic and the line, 3 lines forming a triangle, cuspidal cubic, conic and the line that they are tangential at one point, and I have three lines running to one. Okay? And then I assume lines of the second kind, then I know that if fiber is ramified, it's singular, and I have this huge machinery of neural models, which tells me what will happen on the singular fibers. And on the singular fibers, I can essentially know, I know what are the inflection points or torsion points, whatever you like. So I know that the line of the second kind must run to those points. This is a really severe restriction of the behavior. And then the first observation is if I have an unramified fiber, then it has only 3 possible types. Unramified fiber means that my line runs to 3 smooth inflection points. Yeah, and by this table, those cases are excluded. Okay. Then if I have a ramified fiber, then I have one of those 4 types, and this is more work you have to do base change. Yeah, I'll come back to this in a minute. The fundamental trick which gives you the answer is this observation. The fibers of these types come always in pairs. Whenever you have a triangle, you have to pay with a nodal cubic. Or you have a pair of triangles and you pay with line to fiber. Why? I will now assume that ramification type is 2 squared to make things simple. Yeah? And then at the first step is I consider this diagram. I have my surface and I have the cover. So I put back the surface. Then I have here my line L, and I have on one hand I have the map here and here. Yeah? So this line gives me a section of this surface. Everything is of the second kind. So I will be running through the inflection points of those elliptic curves here, the fibers. So I will put this section to be 0 in order value of this surface. Okay? I made this assumption because I want the cover to be Galois. I want to get 2 extra sections for free. I had a 3 section. Yeah, this line was originally a 3 section of my vibration. After this base change, I got the section to have model value, but luckily I have deck transformations. I get 2 more sections for nothing. And since lines of the second kind, there are 3 torsions inverse to each other. And now I am in very good position. I can use isogenics. So I will divide my surface by this Z3 action and resolve the singularities. a general theory that both surfaces have the same Euler number, for instance. They have lots of invariants in the same. Okay? Yeah?
So there is no map from S to S.
Yeah, I'm cheating. It should be kind of dots. Yeah, yeah, yeah. I knew it. So somebody's not asleep yet. Okay? So now you have to analyze the behavior of fibers. What happens? If I start from I1 that is unramified, I get 3 copies of I1 on S2.
So yeah, I said it's difficult for me to read everything. It's just,
I'm sorry. Yeah. I slightly sped up. I will give another problem.
what is S2? I just.
Okay, sorry. So now I started from S. I pull back the vibration to S2. This is just the surface I obtained from the triple cover given by line. Okay, so this is this one. And then I produce on this surface.
S2 is a fiber product.
Exactly. And then I act with Z3 on this one and obtain an isogenous elliptic surface.
Why is it cyclic?
Essentially because
of distortion transformations. Okay.
yeah. But the fundamental part is this one. If you don't assume this one, then this cover will not be well work. And you have to do extra work. You have to introduce extra curve here. Okay? Yeah, that's the fundamental point of the game. Okay, so now I have to compare fibers. From I1 I get 3 copies of I1 because it's unramified. And then when I divide out I get 2 copies of I3 over this. And it goes as I have written down. This is standard theory. I'm so quick because I just want to explain the idea how we do this. Yeah? But you know that both surfaces have the same Euler numbers. Yeah? Which means that I can compute Euler number using the first union of the first, Euler numbers of the fibers of this one or of this one. And they are equal. So all you have to do is to compare. Yeah? When you compare those two numbers, you will see that U3 equals U1 plus R1 plus twice RT. And this is the claim. For every triangle, I will have to pay either with one ramified or unramified caspital cubic, an over cubic, or with one type 2 fiber. Okay? That's the game. If you have this, you are at home. There's nothing to be done. As Fabrizio was kind to observe, things get nastier if my original map between L and P1 is not going. Then you have to take our closure, the map has degree 6, and then you repeat the game, but you have to control the behavior of components. Okay? But still the argument works. And this gives you the example we essentially produced. Namely, for this type you get 12 lines meeting, this is what Segre was claiming. For this ramification type you have 2 possibilities, and for this one you have 3, with this 20. And the proof is just case-by-case analysis. So for instance, if I have this type of ramification, then each ramified fiber is to be paid for by type 2. Okay? This gives me Euler number 8. I have 16 to sell. Now, if I have a line that is meeting, if I have now a triplet of lines that is meeting my line, then I have to pay with 1 copy of Y1. If I have 3 lines running to a point, then again I pay with Euler number 4. Yeah? So whatever I try, I will get always 12 lines. Okay? The things get nasty in this case because for this ramification I might have 2 I2 fibers in the ramified fibers. This gives me 2 lines. And then I will have to pay for this I2 with 4 I3s. Because this is how it works. Whenever I have an I3, I have to pay with I1. For a pair, I pay with 2 I3s. And then I have still enough space to get either 2 type 4 fibers, or 2 pairs, or 1 type 4, 1 I3, I1. Okay? This is 20. This gives me 20. I don't know that 20 exists. I know there is nothing better. I cannot get more. And then you have to brutally solve the equation given by condition of the second kind, but you have to assume that the ramification type is fixed. Then you can do it. If you got for Christmas a bike, and you have the paper the bike was cracked in, then you start upstairs and keep solving, and then you get solution in the middle of the paper. You can do it by hand. Okay? It's not hard. And then you can just compute discriminant for this vibration. This is absolutely elementary. And you get that you will have the site of two fibers under some conditions, and this is the way we got the counterexample. Yeah? Actually, we wanted more. We wanted as many lines as possible. We wanted 60. So the 60 was obtained by coming to Grassmann variety, studying the reduction of the Fano scheme, and playing over various fields. I mean, the surface is defined over Q, so luckily it was enough to do Chinese reminder to find the surface, and it was cheap. So this is essentially what we get. The bound is 20. If I have more than 18, this must look like that. And if it meets 20, then again you have a condition. What comes for free in this game is an automorphism of the surface, where you have 19 or 20. And this automorphism is symplectic. So now you can play on this family, any kind of game you learned from equaling and Quark, all the guys in K-trees. Yeah? This gives the second theorem. Any characteristic different from 20 works. Here, these two characteristics are excluded for various reasons, but essentially this flecknodal gadget is well defined if your characteristic is high enough with respect to the degree of the equation. This was shown by Volk. He was counting here from point on surfaces, and then he needed this gadget. Okay? If you go to degree 3, you do something different. Namely, you show that there is a common bound on the number of lines that need a conic. The bound is 48 for any field. It is sharp because it works on Fermat. You can find a conic on Fermat that's met by many lines. Okay? And then, in characteristic 3, you may have quasi-elliptic fibrations. This will give you will get 10 type 4 fibers. This gives you 30 lines. And then you get bound of 112, and this surface is unique. It's unique up to PGL for action, and it's unique as a K3 surface, because it has Arden by N1. It's really E1. Example was known already to Segre. So now we have all characteristic by characteristic 2, and we want 2. And here we got beaten by Russians. Yeah? In other words, we were able to show that in characteristic 2, the bound of 64 still prevails. We could show that Fermat has no smooth reduction modulo 2, but we could not exclude some configurations. What we found at the same time was that in characteristic 2, you may repeat bar construction of a quantity with 75 lines to get a quartic with 60 lines, smooth in over characteristic 2. But you can construct the family of K3 quartic with 68 lines. Yeah, I mean, this is what violates essentially Fyodor's question. In this characteristic, you may construct a smooth K3 surface which contains more lines than singular, which is more than smooth. Yeah? It's very strange. It's the only characteristic. And then Alex Ektiarev, using computer, was able to show that 6 indeed is the bound. This is sharp.
If you allow considering cones, definitely.
Oh, yeah. Yeah, but I say K3 quartics. So I'm on the same side. Yeah. Actually, Alex, with Ittenberg and Sertus, were able to show that there is only one complex quartic with 64 lines, there are 3 with 60, there are 4 with 56, 2 with 54, and the rest is at most 52. So now we have a complete classification, yeah, essentially. This is short. Out of these 3, one is the one I have just shown. There is another one, it's unpublished. There is another one that's no longer defined over Q, and I guess the third one is missing. By Torrey type arguments, you know it exists, yeah? But we don't know exactly.
Sorry, I have a question. So isn't theorem 6 weaker than theorem 5?
No, it's stronger.
Stronger.
Here I have 64 at most, and here I have 16. So Alex, I mean, we had some cases we couldn't kill. We couldn't exclude existence of 64 lines on some surfaces, and Alex could exclude existence on all surfaces.
No, I'm reading both statements and I don't understand what
They're different authors, you see.
I mean, theorem 5 is clearly stronger than theorem 6 is written. I mean, I don't
Oh, okay, maybe let's put it this way.
Singularities, yes, singularities. So 60 is for smooth. With singularities you're getting 68, yes?
Yes.
Okay, so that's the point.
68 is not in the theorem, yeah? It's between two theorems.
So the first theorem says, maybe I should say, this one says there are no smooth quartic surfaces with more than 64 lines if characteristic is 2. And this one says there are no smooth quartic surfaces with more than 60 lines if characteristic is 2.
So definitely it is strong.
It's like saying Sławek has only, I don't know, 500 euros and someone says gives only 400 euros. So this is the second thing that's stronger, yeah, because it means you have even less, yeah. Okay?
sorry, I'm
Maybe
very
we
stupid.
discuss it after.
No, but I mean, I think maybe there is a language problem. I mean, when you say a smooth quartic blah blah, do you mean there is a smooth quartic?
No.
A smooth contains.
Any means any. Like every.
Okay, maybe we can discuss
Okay, we
that.
discuss after. I'm sorry, I'm having trouble time. I do apologize. So these are quartics. I mean, if you want now complex quartics with singular points, there was a student of Matthias.
Sorry.
I'm sorry.
I got a problem with at least and the most, but I'm sorry. Yeah, that was the, yeah.
Sorry. Now we had a student
So
in
that was a
Hanover
language
who,
problem.
who kind of repeated those arguments for quartics with singular points, and he got 64 lines. You just get, the vibration gets more complex. You get more fibers. It's more elaborate. But the,
Complex.
yeah, it's complex. Then it somehow, I come from Krakow, and when I was
So what does
master's
it mean? That it has rational double points and singularities.
Exactly. Your ADs are allowed. So in Krakow, I was kind of heavily trained in affine case, and there was no bound for affine quartics. Yeah? So to do affine case, you should also consider non-KP quartics. You allow higher singularities. Then you have a classification. It was done at first by Dichiara with some 2,500 cases, and then there's classification by Jonathan Wall in a published paper in which he gets 4 families. Yeah? 3 of those families are really easy to study. There is one family, he writes, it's really strange that it exists, and on this one we could essentially get no control. So I will never believe that something that is non-K3 with 4 tail exists. No way. I think 31 is the answer. Yeah? But still it's enough for us because it gives you the affine case. Yeah? There's a lot of classical papers on quartics with non-isolated singularities. Yeah? So 64 is still bound if you assume no 4-4 point and you assume that singularities are not isolated, because the quartics that are swept out by lines were classified by Roth and by Italian school, and then it was redone by Jakob, just wrote it very precise way. There is a paper. You got all cases, everything. So these are quartics. There are some. Okay, so this was introduction. now, no, I'm sorry. I'm joking. There are still some open questions, like for instance, I assume non-K3 quartic contains all at most 31, and they always come up with Orchard type configuration. Like if you have now a line which doesn't run to the singular triple point of your quartic, then you take the plane spanned by the line and the point. The residual curve is a cubic with triple point, cubic curve, so it's 3 lines. Okay? In other words, counting lines on K3 quartics with triple points is just solving the classical orchard problem. You have an orchard with you plant trees, 12 trees, and you ask, what is the maximum number of triplets that lie in the same line? I want to have a nice orchard such that when I stand in front of a tree, there are 3 lines, 3 trees in the same line. And the answer is 19 in this case. Such configuration exists, it can be obtained from elliptic curves. This is like from So this is how we get 31. What we don't know is what is real bound if you have K3 quartic surfaces indeed with singular points. We have no geometric arguments for the uniqueness, And what I would like to have, is kind of my hobby, I would like to have a criterion. Somebody comes to me and tells me, so like this is a configuration of lines, and I say, yes, this one is possible to realize on a single port. And there is such a criterion for configurations of AD singularities. Yeah? Okay, so now I have 2 minutes, so I have to dispense.
Have a long break, so maybe. Okay.
Okay, so let's say I have 6 minutes. Thanks. I promised a simple proof for this 20. Yeah? And the proof will go as follows. Suppose I have my line, yeah, on my quartic. Now, in each point, I consider the tangent space and the form given by Hessian. Almost everywhere, the intersection should consist of 2 lines, because they intersect the plane with a quadric. But one of the lines is the line I started from. Yeah, this line must live in the intersection. So actually, when I move along the line, I normally get just one line, with some degenerations. And then I have to check carefully how to find those lines. And this is nothing special. Yeah. You find such funny determinants, and this determinant finds you the ramification points of this map we started from. And then you define these polynomials. I know they look kind of long. So suppose you are on the quartic, then you will obtain 2 functions, b0 and b1. On the quintic you get b0, b1 and b2. Okay? And what do those functions come from? Essentially, you take the equation of your surface, this generator, and restrict to these principal lines. Yeah? Since the line has contact 3, the expansion leaves you with only, say, d minus 3 coefficients. Okay? And the condition for a line to live on the surface is exactly the condition that all those polynomials vanish, or rational functions. Okay? I mean, I don't know why nobody came up with this figure. They were fighting heavily in this subject. This gadget, I call it B function because Professor Bauer doesn't allow me to call something after him, but we spent some time with lines and I want it to be this way. So yeah, I have a line meeting my line on a surface if all of those functions vanish, because essentially it means a polynomial vanishes on a line if all coefficients vanish. Yeah? And then, so this is essentially trivial. And then the line of the second kind is line where B0 vanish. And this beautiful definition by Segre has very simple meaning. So first kind means that when I expand in direction of principal lines, I have something that is the first jet doesn't vanish. Second kind gives you vanishing of the first jet. On quintics, you will get no funny properties for lines of the second kind because you need the lines of the third kind. You need vanishing of the first 2 jets. Yeah? This formulae of Segre obtained using Segre 13 invariants, that each line of the second kind is met by 12 lines and blah blah, this is just basic theorem of algebra. If line is of the second kind on a quartic, B0 vanishes, and the line lives on my surface and meets my fixed line if the second coefficient vanishes. Yeah, but it's a polynomial, so it must have zeros. That's it. Yeah? I mean, this argument, in its triviality, has one huge advantage. It works for higher degrees. The first attempt would be to use elimination theory to play with this. Yeah? And it kind of is a tragedy. You get horrible bounds. But you may do something different. You say you're on a quintic. You start from a line. Then you solve a system of equations on the second jet given by the condition that B0 vanishes. And it's a system of linear equations. You solve it. You get a subset of OP35, and then on this subset you solve the condition that the second jet vanishes. And it's linear. You solve it. You get another solution. And then, in this way, all you have to do is to assess the degrees of those numerators. Yeah? So the answer, I know I'm running on the borrowed time, is that for this is what happens for the case I discussed before using elliptic curves. B0 vanishes and B1 has this form. It has degree 18. And If P0 and P4 vanish, I am producing extra lines in ramification points, and I have a thin away from it, and this is 20. Yeah, I think it's simpler, yeah? And what is even better, I can do it for quintics. For quintics, I have more cases, I have to be careful, but the number is 28. The maximal number of lines that meet a fixed line on a smooth quintic surface is 28.
I see.
This is the second round.
Ah,
First kind. You assume second kind. You have 7 ramification types.
I see.
And then you just compute those V0, V1, V2, you check the degrees, and this is the one. What I suspect, but cannot prove, is that only this case comes up. Yeah, this one is kind of hard to kill, to get below 28, but these two are less convenient because you get huge families of surfaces. Yeah? Out of 7 ramifications, the smaller the family, the better for you. So I cannot control these two, I just get 28, I can do this. Yeah? So in general, then you can of course say when you get this high number, and this is this one, or this one, and of course you may say, okay, is it sharp? And it's sharp, it's easy, because you take this family, you solve the systems of equations from the coefficients, and you get 28 meeting a line. Yeah? This is done here. Oh, it's horrible, I'm sorry. It's huge. But it's absolutely cheap. You just get conditions, you plug them in, you check the surface is smooth, you get 28 lines. Okay? This somehow shows that these gadgets will never get you below 125. Because originally I wanted to count the lines on quintics. Doing this purely topological arguments, I can get counted 29, because it's hard to control the situation when you have a line that is not met by 4 coplanar lines. Yeah? Somehow there is a discrepancy between topology and algebraic geometry on quintics. On quartics, on K-trees, it's really close. It's easier, yeah? But using Bogomolny Aukayao, you can get below 28 for this non-coplanar case. So the bound will be 125. We don't know that it's sharp. We have 3 families, one of which is really juicy. And when I have time, maybe I'll write a script and try to look for something with more than 75 lines. This is the best known example.
Say it again.
The best known example has 75 lines. This is Fermat and Bar-Quintic. Yeah? It's open where the lines generate, for instance, Picard group of a smooth quintic. Let's put it the other way around. Whether the bound given by Lefschetz theorem of 1-1 classes is sharp. Whether you can construct a quintic surface with Picard number 45. Smooth one. Yeah? So I ran some tests, and I believe there is some hope that this one also would work with this. Okay? So I stole 5 minutes. I have some stuff.
Okay, thank you. So at the moment I understand that there is a discrepancy between 75 and 125.
It's a big discrepancy.
Okay,
I mean, sextics should be kind of cheap because there are good examples on sextics. But somehow I'm not a fan of solving linear equations. It's nice, but.
I have 2 questions. One is a practical question. I mean, maybe I would like to ask both the people who will talk if they can make their transparencies, beamer presentation available.
It should be global.
And the second question is the following. I mean, essentially, it seems to me that, so, like the generate quartics, there are also double covers of P1 times P1, okay? So, now if you have essentially if you have 2 skew lines on the quartic, then you have a double cover of P1 times P1 automatically. So, essentially, you're using elliptic, but you could also use this double covering method. And my question is whether for quintics, when you have these 2 skew lines, then you will get the triple covering of P1 times P1, and whether you ever try to use triple coverings theory to approach the situation.
Yeah, I tried a little bit. I had problems with singularities. For double covers, this is how Alex constructed some equations of the surface.
Yeah, because it's a,
I know. It's very
it's a
handy.
limit of the general Kummer in the sense.
You're right. We made a try and somehow didn't work well. It doesn't work. Yeah, maybe I'll come back to the problem. But you're right. One can try. For quartics, this is a trick. One of the tricks you use to construct examples. Exactly this cover. Right. You have to do this joint. You do this cover. You are able, you do at first computing lattice theory, you get a lattice, you find minus two curves, two of them are disjoint, you have some extra conditions, you go to the cover, you translate conditions into behavior of the branch curve to get the surface. So this is the general philosophy.
So the branch curve will be of type 4, 4, yeah?
But sometimes it splits, yeah? And then you're happy.
Other questions? No? Then let us start again.